Let's continue the story we developed in last video about a person A and B and a message M and insecure network in between, which is internet. Okay, and then we'll now see how we do encryption basically. So this was actually our last drawing basically. Let's move. What we'll do, we will first explore some key concepts as they are without going into much technical details in it. In CISSP, you don't go into the technical depth of any technology, but you know the overview of the technology, how it works, and what it means, like what business objective we can achieve with it, right? So there's some key concepts. So the key concepts is like this. If you have a message M, this message M can be encrypted with a key. So you have a key, you apply the key on message M, and the M will be an encrypted message M dash. This is encrypted. So when I say M dash, it means an encrypted message. And when I say M, it's unencrypted, and it's called plain text. Plain text. And key, we will refer key as K. It's better to say K plus M is M dash, and this will be key, right? Now, if a message can be encrypted with a key K, it can be decrypted with the same key. So if I have a message M dash, and then we apply a key K, we will get the same message M, which is my plain text, right? So this is one fundamental formula that a key can be used to encrypt and the same key can be used to decrypt. If this formula is something which we are applying anywhere, this is called symmetric cryptography. This is called symmetric encryption, basically. So in symmetric encryption, you have a key which is used to encrypt the message, and the same key is used to decrypt the message, right? So if you know this concept will also be used in asymmetric encryption as well, but with a different method. So in symmetric encryption, the basic thing you have to remember is that you have a message M and you have a key K, and the same key is used to encrypt as well as decrypt the message. Okay, so how it will work in our scenario? So in our scenario, we have a user A and we have a user B, and we have a message M, and then let's take some other color. We have internet, and we want to send this message from A to B. Now, how it will work is that there will be a key K, which is a key. This key will be applied to message M, and then we will be having a message which is M dash, right? Now this M dash will be transported to B, right? Now B is having M dash, But how it will decrypt? To decrypt it, remember this formula? That if there is a message M, we apply K, then it becomes encrypted message. We need the same key to decrypt the message. Now, to get the same key, the key also has to be transported to user B, right? But here we have a problem. We had a user C here, which is basically the bad guy. Now he can intercept message and he can intercept key. So there is no security here, right? So if B can receive M dash and K, and basically what it can do, it can use K plus M dash and it can retrieve the message M, right? Same thing C can do. C can also have M dash. It can have K and can receive the message M. Then what's the point? There's no point, right? Now this problem is called the problem of key exchange. This is called the problem of key exchange. So in symmetric key cryptography, since you have the same key for encryption and decryption, the key has to be transported to both the parties, A and B. And when you do that, it has to be out of band. If there is an out of band setup, or if there is a secure path where you can transport the key. But the thing is, if you have a secure path to transport the key, why not to transport the message itself to the secure path? Then you don't need encryption. So you are in a, not exactly, but you are in a chicken and egg problem, that you have a message M, you want to encrypt with a key, but how you will transfer the key, right? Now to solve this problem, there was this scientist Diffie and Hellman. They actually kind of devised this method in which both the parties share some random prime numbers, and it generates a key which only A and B knows. This was a magic mathematics. It's called Diffie-Hellman algorithm. Now, I won't go into the details of Diffie-Hellman algorithm, but the way it will actually look like is, again, let me draw this here. You have internet, and then you have A, user B, and an attacker C. Now, they will exchange some random numbers X, Y, Z, T. And based on the number exchange, they will develop some key here, K1, and the same key will get generated here. But this key will not be visible to the attacker C. And how it happens, it's a mathematics based on modulus operation. I won't go into that detail to make it more complex, but at this stage, you just remember that it happens that the same key is generated at both sides, but C can't actually intercept that key. So in this way, we can encrypt the message M with K1 here, get M dash. This M dash will be again transported to B. It will apply the same key K1, and you will have message M here. And since attacker don't have this key K1 with him or her, the decryption will not be possible for C. So this is symmetric cryptography. Now, this symmetric cryptography is it's not like it is not used. It's used today as well. I will tell you where it is used. But this is the way it works. Now, few things here, like what this symmetric cryptography is achieving. Since it's encrypting the message, so it is basically upholding confidentiality of the message. This is something which you have to keep in mind. As I said in my last video as well, that wherever there is encryption, it means its prime goal is to achieve confidentiality of the message, right? But as you see that it's not, there are many problems with it. One of the problem is I said that the key exchange, even though you have Diffie-Hellman, there are ways it can be intercepted. So it's not that secure. Other thing is that in symmetric cryptography, you need one key per communicating party. So if you have a legitimate user here, D, then you need one pair of key between A and B, one pair of key between A and D, and one pair of key between B and D. So the total number of keys, the formula will be n into n minus 1 divided by 2. So this is how the number of key will increase if the participants keep on increasing. Now, coming to the asymmetric approach, in asymmetric approach, basically things look a bit different because we don't have the same key for both encryption and decryption. We have different keys for encryption and different key for decryption. And we will discuss that in the next video. And then we will try to see the original question, which I actually I put forward, that what will be the scenario where we will be encrypting the message, but we won't be concerned about the confidentiality of the message. Again, think over it. Those who have already covered the course of cryptography may have the answer, but if you don't, just try to think the scenario in which you will be doing an authentication of the message, but confidentiality will not be will not be achieved, and this authentication will be with some sort of encryption, of course. So encryption without confidentiality, what will be the scenario? With that question in mind, let's move to the next video, where I will be explaining asymmetric key cryptography in details. Okay, thanks for watching the video.